Hello everyone, good morning, good afternoon, and good evening. Hope you're all doing well. Hope your family, your friends are all doing good in this crazy ass time. And hopefully we're all keeping ourselves busy, keeping ourselves mentally and physically well as well. So, just want to reiterate with what Matt said last week. Unfortunately, with everything that's going on, as I'm sure you'll know, we will not be coming back to Kings for the time being. So we will be uploading all of these solutions to the questions up onto either Keats or to YouTube, as Jeff has done previously. But again, if there's anything that we can do differently that you would prefer, or if there's another way that we can explain certain things that would be easier for you, please do let us know, and we will try and accommodate that. And in any case, if there's something that you're not too sure about, so you don't quite understand, after the lectures or after the problem classes, do let us know, send us an email, and we'll be happy to help as well. So let's dive into it. For these questions, I will try my best to do all of them within an hour, within the time frame. And I think what would probably be best is to start off with question 2, because question 2 will tie quite nicely into question 1, and we'll need to use the relation that we will show in question 1 as well. So let's get started. So first of all, question 2 says, show that de Broglie's requirement for standing waves in the Bohr model of an electron orbit in the hydrogen atom gives the electron's angular momentum L as L equals nh bar, where n is some positive integer from from 1 upwards, and h is a reduced Planck's constant. Okay, cool. So first of all, just a quick recap of what you probably would have seen in Jeff's lectures on YouTube. I believe it should be part 1 of his video series. But anyway, just to recap, we have some nucleus that has some charge Ze, positive Ze, sorry, and we have an electron that's orbiting around it here. So this is kind of like a semi-classical approach where we have essentially like a solar system model. We have an electron that is orbiting circularly around some positive nucleus. Now, as you know, that de Broglie's relation states that matter behaves not just as particles, but also as waves, where its wave relation is given as the wavelength of that particle is equal to the Planck's constant divided by the momentum of it. So what we're essentially saying is that this electron here is behaving as a wave that is oscillating around a nucleus, a central nucleus here. So what does that mean? Basically, we can say that, or at least what de Broglie has said, that this wave must be oscillating around this nucleus as if it was a standing wave, where if you were to unwrap this wave behavior, it would look something like this. Something like that. It's poorly drawn, but you get the point. So what does that mean? Essentially, it means that the whole length of this must be the circumference of our orbit of the electron. So that's given as 2 pi r, where r is the radius of this circumference. And the other condition that we must have is that at the points of these ends, they must be in the same phase. So if, for example, we have a sine wave at this point and at this point, they must both be at 0. It doesn't make sense for our electron to have some wave behavior where there's some discontinuity at any point. It doesn't really matter where, but at some point of our orbit. So what does that mean? It means that for our wavelength, we must be able to fit whole integer numbers, a multiple integer number of our wavelength within this 2 pi r circumference distance. So it means that we need to fit some multiple integer n of our wavelength into our circumference here. So we have n lambda equals 2 pi. So now that we have that, The other thing that we also need to know, or at least use, is the angular momentum of this electron. So you know from classical mechanics, classical physics, that if we have some particle, doesn't really matter what, it could be anything, that is on some curved trajectory, so it has some velocity v going in this direction, and it has some instantaneous radius curvature r here, then the angular momentum of this particle is simply the mass of that particle multiplied by v vector cross product r. Now in this case, because we're dealing with circular orbits, we know that r and v must be perpendicular to one another, and as a result we know that the vector L is just the magnitude, which is essentially just v times r, like so. So that's what we want. We want, let's just call it L, this relationship here. So combining all of that together, we have L is equal to mvr, n lambda is equal to 2 pi r, and lambda is equal to h divided by p, where we can just say lambda is just h over mv, where we've used our classical momentum relation, p is equal to mv, or momentum equation anyway. So putting that all together, what do we have? Well, let's say we have, let's say we put these equations as numbers. Let's say we substitute 1 into 2, such that we have nh divided by mv is equal to 2 pi r. And so as a result, we also have mvr equals L. Let's just put that down here. Rearrange this so that we have nh divided by 2 pi is equal to mv of r, and that is also equal to L, as we also know from before. What does that mean? Our angular momentum of this particle is just equal to n times the Planck's constant divided by 2 pi, which is also equal to nh bar, where we know that h bar is equal to h over 2 pi. And that is exactly what we want from the question. Oops. Like so. Easy. More or less. Okay. Next question. Show that for the first circular orbit, using principal number, quantum number n is equal to 1. So let's highlight that. Let's highlight it properly, actually. There we go. In the Bohr model, that the fine structure constant alpha can be obtained as alpha is equal to v over c, and that's also equal to 2 pi ke squared over hc, and we have a bunch of explanations for what the constants are. So let's just write that down now quickly. K, as you will find, especially in your later years, particularly in optics and electromagnetism, that this K is equal to 1 over 4 pi epsilon naught, and it's found in a lot of places. We will deal with that quite a lot. Anyway, E is the electron charge, V is the electron speed, C is the speed of light, and H is the Planck's constant. Right, so let's just bring down what we've written above here, this thing, because we'll need to use that. So L is equal to mvr, which is also equal to nh over 2 pi, or nh bar if you like. Now we've already been told that our principal quantum number is just 1, so anywhere there's an n we can just ignore it, basically. Okay. So you're probably wondering what actually is the fine structure constant, otherwise known as the Sommerfield's constant. And I'm not sure if Jeff has explained this or mentioned this, but it's not something that you need to know explicitly or specifically, but it's probably something that you probably should have an idea of, just so that you know exactly what you're answering in this question. But it's essentially, it has a lot of different physical interpretations to it. But the thing that we need to know in the context of this question is essentially the amount of scaling, or the scaling at which the spectral lines, the atomic spectral lines, splits due to relativistic effects that is introduced into the Schrödinger equation, or at least when we're trying to solve the Schrödinger equation. Because remember, the Schrödinger equation is a non-relativistic treatment of an electron that has no spin with it. However, to get a more accurate representation of what's actually happening to the electrons within an orbit, within a nucleus, within an atom, we need to treat it as a relativistic particle that has a spin, and this is where the fine structure constant comes in. You'll find that in the later years, particularly next year, you'll be doing an experiment that deals with the Zeeman effect, which is essentially this, the splitting of atomic spectral lines due to an external magnetic field. Another similar effect is essentially the Stark effect, which is the same thing, but using electric fields rather than magnetic fields. It's quite a lot of information. You probably don't need to know all that, but anyway, just to give you an idea of actually what it is, very briefly, at least I think will help. So let's get stuck into answering this question. So the question first says that in the first circular orbit, so that gives you a clue already. So a circular orbit, again, I'm going to draw another picture. Same picture as before, we have our nucleus with some charge Ze, and our first circular orbit that is stable, that has a negative E charge. So that's our electron, and this is our nucleus inside the middle. Here we could probably just treat it as a hydrogen or a hydrogenic atom, where the charge of the nucleus is just 1. So we can just ignore that. But anyway, the key thing here is the fact that we're dealing with a circular orbit. So we're going to use some classical physics as well to treat this. Now, because of the fact that it's the first stable orbit, as postulated by Bohr in one of his postulates, we have to treat this as if we have forces acting on this electron. Now, what are the forces? Well, because of the fact that we're dealing with charges, we need to deal with the Coulomb force. And also, because of the fact that it's a circular orbit, we also need to deal with a radial force here, or the centripetal force. Now, the Coulomb force, what is it? So force, let's say Coulomb. I'm not going to deal with vectors. Obviously, you should include vectors all the time. But for now, because of the fact that the forces are all... the components are all orthogonal to each other, we don't really need to deal with it for now. But anyway, the force that is due to Coulomb is equal to Ke, or 1 over 4 pi epsilon naught, as mentioned up here, multiplied by one charge, multiplied by the second charge, or divided by r squared here. Whereas in this case, we can just treat both of the charges as equal. Here. Notice I'm also ignoring the negative sign as well, because I'm not actually interested in the direction or anything like that. I'm only interested in essentially the magnitude of the vector force here. Just to note that because of the fact that this force is also negative, technically, this force is also attractive. So as you know, opposite charges attract. This is why. Right, anyway. Next, we want to deal with the radial force here. Now, that's just the centripetal force. And you'll know from classical mechanics that you've probably done in high school, or at least in your other maths classes, the force due to radial motion is just the mass of the particle times v squared divided by r, where we know that the acceleration, the angular acceleration, is just v squared divided by r. And that's how we get the relation F equals ma, therefore mv squared over r. Now, since this is a stable orbit, what we need to do is we need to equate these two forces, these opposing forces, together, because otherwise if we have a net force, it's not stable, and we don't get a stable orbit. It's as simple as that. So we get mv squared divided by r is equal to ke e squared divided by r squared. Right, now from this equation up here, from that equation, we can solve for r, ignoring L. So I'm going to write it down here. Just divide both sides by mv. We get nh over 2 pi mv over here. So we have this equation. And then down here, I'm going to solve this equation for v squared. So I have v squared on the left-hand side, multiply top and bottom by, multiply by r divided by m. So on the right-hand side, we get e squared still, divided by mr, like so. And so what I can do now is I can substitute this r into this v squared to get ke 2 pi mv e squared divided by hr. No, sorry, not hr. mh. There we go. Where I'm just ignoring n, because I know that n is equal to 1. So m's cancel out. V's also cancel out. Oops, sorry. So what are we left with? V is equal to 2 pi ke e squared divided by h. And so simply dividing by c's on both sides, what we're left with is the fine structure constant is equal to v over c, and that is 2 pi ke e squared divided by hc, which is exactly what we need. If you want, you can also just reduce it even further and call this h bar c instead. And that's also fine. And that's it. That's the first question done. Let's add a page. There we go. That was easy. Now, what is the next question? Plug in the values and the SI units of the constants Ke, E, H, and C to show that alpha is unitless and calculate its value. Right, so part B. Let's write this out again. Alpha is equal to Ke E squared over H bar C. Right, so I'm just going to write down individually what each of these constants are. So these are only approximate, they're not exact, unless they actually are exact. But anyway, K is approximately 9 times 10 to the 9. The units are joules meters per coulomb squared. E is equal to about 1.6 times 10 to the minus 19 coulombs. H and H bar have the same units just because of the fact that they're divided by 2 pi, which is unitless, so we don't need to worry about that too much. Is 6.626 times 10 to the minus 34 joules. Joules seconds. And lastly, the speed of light is about 3 times 10 to the 8 meters per second. Like I said, only approximate, is not exactly 3 times 10 to the 8, but anyway, doesn't really matter. Okay, so for now, I'm just going to ignore all the numbers, and I'm only interested in the units of alpha. So ignoring all the numbers, K has units of Jm per c squared. E squared has units of c, but squared. H has units of j seconds, and C has units meters per second. Right. So what does that equate to? What does that cancel down to? So we have J's at the top, and bottom, they cancel out. We have meters on the top, but also bottom, they cancel out. C to the -2, but that cancels out with the C here, so these two cancel out. And lastly, we have seconds multiplied by per second, and so finally we are left with no units, so units of 1, essentially. So that already shows that in that question, we have the fact that alpha is unitless, and now we can just plug in the numbers. Nice and simple, it's literally just punch in numbers into your calculator. 6.626 times 10 to the -34 times 3 times 10 to the 8. If you plug that into your calculator, you should get something along the lines of 7.29, something like that, times 10 to the -3. Again, unitless, so there's nothing here. And very often what you'll find is that alpha, sorry, this should be alpha, not the units. But very often what you'll find is that alpha is actually approximated to be 1 over 137. So later on in your physics career, whether you choose to do research or not, doesn't really matter. But anyway, you'll very often find that alpha is just approximated to be around about 1 over 137. Now, like I said previously, that alpha has many physical interpretations. And one of the interpretations of alpha is that it gives us an idea of what is the maximum charge that a nucleus can have while still providing a stable orbit for an electron within the confines of the Bohr model. And as a result, what you'll find is that the maximum charge is actually just, or about, the reciprocal of alpha. And so the maximum charge that a nucleus can have is 137 whilst providing a stable orbit for an electron, whilst the atom itself is still stable. Why this is the case? It's quite complicated. It does require a little bit more theory than what can be provided in the scope of this course, but essentially this is one of the interpretations of alpha. So it's not just something that's plucked out of thin air, but it does have a physical meaning behind it. Anyway, enough of that. Let's move on to the next question. Question number 3. Show, using the L's and ML quantum numbers, that the angular momentum vector L inside the hydrogen atom can never point along the z-axis. Right, so again, the same thing. You'll probably be given these equations by Jeff, where we have the magnitude of the angular momentum is given by L times L plus 1, all under the square root, multiplied by h bar. And same thing with the now z component of the angular momentum is given by now the ml quantum number multiplied by h bar. And we're told to show that the L vector can never point along the z-axis. Right, so first of all, what values can L and ML take? Well, L can take on values 1, 2, 3, blah, 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 all the way up to the principal quantum number -1. And ML can take on values within the interval of -L and L, as long as they're integers. All right, so that basically means it can be -L, -L plus 1, blah, 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 all the way up to 0, 1, 2, all the way up to L, essentially. Okay, so why can they not equal each other? Right, so a couple of ways of demonstrating this. First, let's just take the largest value that ML can take, which is L, right? So let's just say ML is equal to L. So what that means is that our second equation here, Lz, is essentially now L h bar. Now, if we assume, let's just say that L can actually equal Lz. Let's just say the angular momentum, the magnitude, can be equal to the Lz component. All right, so if that's the case, what does that mean? Well, it means that we have on the left-hand side, h bar multiplied by L plus 1 is equal to, well, again, let's just take the maximum value that L can be, L h bar. Right, well, h bars cancel out, and we're left with this equality, L plus 1, or under square root is equal to L here. Now, this should strike you firstly because of the fact that this is not actually an equality, right? There's no values that L can take other than L equals 1 that will satisfy this equation. So if we're ignoring L equals 0, so we're not going to bother with L equals 0, let's take it on all the other values that L can take, then it means that it's contradicting our original statement that L is equal to Lz, right? Because if this cannot be true, then it means that this also cannot be true, right? Now, separately though, if we consider L equals 0, well, that's not exactly a unique solution. That's quite trivial, right? We're just literally saying the left-hand side is equal to 0, which is equal to 0, right? Which also means that the angular momentum is equal to 0. But if the angular momentum is equal to 0, then that means our electron isn't actually orbiting a nucleus, which can't be true if we're considering stable atoms, essentially. Right, so conceptually speaking, Lz cannot be equal to the magnitude of the angular momentum of our electrons because it doesn't actually fit in our model, in the Bohr model, essentially. Right, it doesn't make any physical sense for us to have a 0 angular momentum but still have an orbit of an electron. So they're incompatible, essentially. Logically speaking, they don't make sense. Same thing, similarly, we can also take the diagram that you would have seen in Jeff's lectures, where we have the Lz component pointing in this direction, and we have the possible angular momentum states, L here going this way or this way. Right, depending on whether the L equals 1, for example, L equals 0, or L equals -1. And we have the angle between the two, right? So we know that the cosine between the two angles must be equal to Lz divided by the magnitude of L, which is ml divided by square root of L plus 1, right? So for for theta to equal 0, we need this side to be equal to 1, right? Because we know that from trigonometry, our cosine behaves as sorry, not equal to 1, my mistake. Sorry, no, it is equal to 1. Yeah. So for cosine of theta to equal 0, which is up here, sorry, theta to equal 0, we need the cosine of 0 to equal 1 up here. But given the fact that ml and L can only take on certain values, there is no combination which allows us for this ratio to equal to 1. So already, mathematically speaking and principally, this statement here cannot be true. And that's it. That's all we need to say. Okay. Cool. Right, and lastly, let's move on to the next question, which is the Heisenberg uncertainty principle. So in terms of delta x and delta p, show that for an electron in a circular orbit along the xy plane, that this relationship holds. What are phi and L? Phi is the electron's angular position, and L is the magnitude of its angular momentum. Right, so let's break it down a little bit. So again, as per usual, we're only considering non-relativistic cases, right? Because any time we add relativity into quantum mechanics, things start to get a bit annoying. So let's ignore that. Right. So first of all, let's consider the angular momentum. Angular position. This phi here. Well, what is phi? Because of the fact that we're dealing now with circular orbits, it no longer makes sense for us to deal with the situation in terms of our regular xy coordinate basis. Right? There's no point in trying to tackle this problem using our Cartesian coordinates. Instead, let's change it now to using, so if I do dotted lines, instead let's use this new basis, r phi, which is our polar coordinates, right? Same thing, we can still specify any points along the 2D space with, again, two coordinates, r and phi here, just like how we can specify x and y along a two-dimensional plane in a Cartesian coordinate system. So in this case, the angular position is simply, if we're considering r to be constant, because we know that from, again, the first postulate, that electrons orbit around a nucleus in a stable orbit, and if it's stable, it means that r, the radius, must be constant throughout. Then we can simply specify the position of an electron for a given orbit as just phi, using just the coordinate phi, right? So let's write it down here. We have some radius r, some position phi. Now, obviously, if we're going to consider it from the horizontal, this is just sweeping a small arc length from the horizontal up to this position here, which can go around all the way until 2 pi, essentially. Now, what does that mean? Well, we have this little distance here, s, and from geometry, you'll know that this s is related to the radius and the angle at which this radius makes with the horizontal as s is equal to r times phi. You're probably more familiar with seeing it as something like the arc length is equal to the radius times theta, something like that. But same thing, right? Exactly the same thing. So phi is equal to s divided by r, essentially, right? And equally, because of the fact that we're dealing with non-relativistic cases, we can just take the momentum of our particle to just be the mass times its velocity, right? We don't need to worry about the relativistic effects in momentum. We don't need to care about gamma or anything like that. Now, since this is just a linear momentum, we also need to consider a case where our angular position is also linear. Now, you might be wondering, how on earth do we do that when we're trying to reconcile a linear concept to an angular concept? Well, in the grand scheme of things, you can't. However, in cases where we are only considering very, very small chunks, very, very small, infinitesimally small, say distances, for example, we can approximate it to be linear. All right, so if we zoom in closely enough into this tiny little subsection, we can almost say that the distance traversed by this particle along this arc is approximately equal to the distance traversed by some linear amounts, let's say delta x, for example, here essentially we're talking about the tangent along this arc. So because of the fact that now we can take this into account, the fact that we're now dealing with linear motions, we can now also coincide that to our linear momentum, p. I've already written it at the top, I don't need to write it again. So, as a result, because we're dealing with delta s, right, and not delta x, well, it means that we also need to take into account delta phi divided by r. Now, like I said, r, we're going to, sorry. Now, like I said, r we're going to take into account as being constant because we're dealing with stable orbits. We're not too worried about r changing, except when it changes discretely. But for all intents and purposes, we're only going to take into account one orbit. So this is the form that we want. And same thing here. We have the change in momentum is equal to our mass times the change in our velocity. Yeah, okay. Now, here we... Now, here you'll notice that we're missing a piece. We're missing L, right? But that's okay, because again, same thing, because of the fact that we're dealing with such small distances traversed by this particle along our radius, along the circumference, we can also say that L is equal to mvr. Well, then, in that case, if we take delta L is equal to m delta v times r, and then we divide both sides by r, that is the same as just delta p from the top. Okay. Let me just quickly rewrite that. Approximately equal to delta x divided by r. So now we can put this together from our previous Heisenberg uncertainty principle. Delta x times delta p is greater than or equal to h bar divided by 2. Then substituting this into that, and then our delta p also into our uncertainty equation, then what we get is r times delta phi, which is our delta x, multiplied by delta L divided by r. That is just equal to delta phi, delta L, because the r's cancel out, which must also be bigger than h bar divided by 2. And that is the relationship that we should get. Exactly. Cool. So that's all of the questions done. I hope that's insightful. I hope that's helpful for you guys. Like I said at the beginning, and just to reiterate from what Matt said, if there's any problems with the problem classes, something that you don't understand, or something you want us to try and explain a little bit further, or even better, if I didn't explain it well enough now, do give me or Matt an email. Let us know, and we'll try our best to help you. Like I said, again, hopefully you guys are well. Hopefully you guys are keeping yourselves physically and mentally healthy, going out for walks as and when you need to. Obviously staying away from everyone as much as you can, and everything as much as you can. But again, if there's any questions that you need, do let us know, and we will help you. Cool. Great. Thank you very much, and hopefully we'll see you again soon.